Next, we will consider the second case, that is a P1 less than P0. If P1 less than P0, then 1 minus P1 is greater than 1 minus P0, right? Which implies 1 minus P0 divided by 1 minus P1 is less than 1, and also P1 divided by P0 is less than 1, right? Which implies P1 divided by P0 into 1 minus P0 divided by 1 minus P1 is less than 1, right? So here we need to find most powerful test, right? For that, we know that under H0, likelihood under H0, the likelihood is P0 divided by 1 minus P0 power summation xi 1 minus P0 power n, right? Then under H1, likelihood is equal to P1 divided by 1 minus P1 power summation xi 1 minus P1 power n. So we know that we reject H0 for the large ratio, right? So here we will take the likelihood ratio of likelihood under H1 and likelihood under H0, right? It is a likelihood under H1 divided by likelihood under H0, right? So here we will write the value corresponding to likelihood, okay? That is a likelihood under H1, that is a P1 divided by 1 minus P1 power summation xi into 1 minus P1 power n divided by P0 divided by 1 minus P0 power summation xi 1 minus P0 power n, which is greater than K1, right? Which implies 1 minus P1 divided by 1 minus P0 power n into P1 1 minus P0 divided by P0 1 minus P1 power summation xi I1 to n, right? So then here we need a function of a random variable, right? So similar, like you want to take log on, take log on both side, then which implies summation I1 to n xi log of this value, that is P1 divided by P0 1 minus P0 divided by 1 minus P1 power, there is no power, right? Here we take log, right? So there is a summation log this term, which is greater than K2. Here K2 equal to log K1, right? Here this value is less than 0 or greater than 0. Here we know that P1 divided by P0 1 minus P0 divided by 1 minus P1 is less than 1. In the case of P1 is less than P0, right? See, this value is less than 1, then log of this value is less than 0, is a negative value, right? So which implies summation xi is if we dividing a negative term, then its sign changes, right? Then it is less than K2 divided by log of this term, that is P1 divided by P0 1 minus P0 divided by 1 minus P1, right? This term, that is which implies summation xi I from 1 to n, which is less than K, right? Which is less than Then the test for testing. Then the test for testing H0 versus H1 is the test for testing H0 versus H1 is phi of summation xi 1 if summation xi is less than k, gamma if summation xi equal to k, 0 otherwise. Here it's a here in this critical case we are using a randomized test, right, where k and gamma are determined by size of the test. That is where k and gamma is determined by expectation of phi of summation xi, that is equal to alpha, right. From this test function we can write size of the test is probability of summation xi less than k plus gamma probability of summation xi equal to k is equal to alpha, right, plus 0, right, equal to alpha. So let me take a summation xi as y. Okay, take summation xi equal to y. This implies probability of y less than k plus gamma probability of y equal to k equal to alpha, right. So here we write the term in the form of cumulative density, right, because here we need to find out the value of k and also the value of gamma, right. We can write this term as a probability of y less than equal to k minus 1. It is same, right. Here y is less than k, then which is same as y is less than equal to k minus 1, right. Here y less than k means it contains value y equal to k minus 1, y equal to k minus 2, so on, right, which is same as, right, this term y is less than equal to k minus 1 plus gamma probability of y equal to k equal to alpha, which implies probability of y less than equal to k minus 1 is less than or equal to alpha, right. Then we want to write the CDF table. Here you know that x follows Bernoulli with the p, then summation xi follows binomial with parameter n comma p, right. Then CDF table is y probability of y equal to y CDF. Here what is the probability of y equal to y? That is binomial n comma p, right, that is ncy p naught power y 1 minus p naught power n minus y, right. Here we need to take the value for y, right, then obtain density and also calculate the CDF. So here start from 0 1 2 so on k minus 1 and k is the density of y equal to k. Then this is a cumulative density, that is a p naught y less than equal to k minus 1, which is less than equal to alpha. Then here cumulative probability exceeds the alpha at first time, then if cumulative densities exceed this alpha value, then at the first time, then the corresponding value of y equal to y is k. Okay, that is cumulative probability exceeds alpha at first time, then the corresponding value y is k. Okay, then using this equation, that is using star this equation, we want to obtain what is a gamma, right? From star gamma equal to, what is gamma then? Gamma equal to alpha, gamma equal to alpha minus this value, right? Then divide by this gamma equal to alpha minus probability of y less than equal to k minus 1 whole divided by probability of y equal to k. Probability of y equal to k. So this is the gamma value. Right. Next, we will go for another discrete distribution, that is a geometric distribution. Okay, the question is given a random sample of size n from geometric P distribution, construct most powerful test for testing h naught p equal to p naught versus h1 p equal to p1. Okay, here also two cases, that is a case 1 is p1 is greater than p naught, and second case is p1 is less than p naught. Here the question is given a random sample of size n from geometric P distribution, construct most powerful test for testing h naught p equal to p naught versus h1 p equal to p1. Okay, so we will consider the first case, that is a p1 is greater than p naught, right? If x follows geometric P, then what is the likelihood then? Under h naught, likelihood p naught x equal to, what is likelihood then? That is p naught power n, then 1 minus p naught power summation xi, right? I1 to n. What is the likelihood under h1? Likelihood under h1 equal to p1 power n 1 minus p1 power summation xi I from 1 to n. Alright, here we know that we reject h naught for the large ratio, right? There is a rejection region is equal to likelihood under h1 divided by likelihood under h naught, which is greater than k1, right? Which implies here we will substitute the value of that. It is a likelihood under h1 is p1 power n 1 minus p1 power summation xi divided by p0 power n 1 minus p0 power summation xi, which is greater than k1, right? We can write this term as a p1 divided by p0 power n and 1 minus p1 divided by 1 minus p0 power summation xi, right? It's greater than k1. Here p1 is greater than p0, right? So this is a positive term, p0 p1 divided by p0. So we can use we can divide by the term itself, right? Which implies that 1 minus p1 divided by 1 minus p naught power summation xi is greater than k 1 divided by this term, that is p1 divided by p naught power n, right? You can take this term as a k2, this term, that is which implies summation, what is that, which implies 1 minus p1 divided by 1 minus p naught power summation xi is greater than k2, right? So here we need to find out whether the, here we want to find the test function, right? It is a function of here xi, right? So for that we have to take the log, take log on both side, then which implies summation xi log 1 minus p1 divided by 1 minus p naught, which is greater than k3. That is what is k3 then? K3 equal to log k2, right? So k is in the case 1, that is p1 is greater than p naught, p1 is greater than p naught, then 1 minus p1 is less than 1 minus p naught, right? Which implies 1 minus p1 is divided by 1 minus p naught is less than 1, right? And then the rejection region summation xi, rejection region summation xi I want to here 1 minus p1 divided by 1 minus p naught is less than 1, right? That is this value is less than 1, then log of less than 1 value is this is less than 0, it's a negative value, right? Then if divided by these term, then the sign changes, right? That is then the rejection region becomes summation xi is less than k3 divided by log 1 minus p1 divided by 1 minus p naught, right? Which implies summation xi is less than ki from 1 to n, right? Then the test for testing, then the test for testing h0 versus h1 is phi of summation xi equal to 1 if summation xi is less than k, gamma if summation xi equal to k, which is because it's a discrete case, right? So we can use a randomized test, which means the critical function takes the value between 0 and 1, right? Then 0 otherwise. Here also we have to we want to find out the value of k and gamma, right? Where k and gamma is determined by the size of the test, right? That is phi of summation expectation of phi of summation xi under h0 equal to alpha, right? Here which implies the probability of summation xi is less than k plus gamma probability of summation xi equal to k equal to alpha, right? So let me take y equal to take summation I1 to n xi equal to y. Okay, if x follows geometric with p, then summation xi follows negative binomial, right? negative binomial n comma p, right? So which implies p naught y is less than k plus gamma p naught y equal to k equal to alpha, right? Which implies here also we need to find out the CDF table, right? So we can write this term as in the CDF form, that is probability of y is less than equal to k minus 1. Here y equal to is y is less than k, right? So we can write that as y is less than equal to k minus 1, which is less than or equal to alpha, right? From the CDF table we can determine the value of k, right? So for that you want to write the CDF table. From the CDF table we can determine the value of k, right? So here y density and CDF, right? Here y equal to y, that is what is the PMF of y, negative binomial, it is n plus y plus 1 c n minus 1 p naught power n 1 minus p naught power y, right? So here also we need to take the values of 0 to k, so on k minus 1 k, right? Then here we will get the value density of k, and here it's a cumulative density of y is less than equal to k minus 1, right? Which is less than equal to alpha. That means the cumulative probability exceeds this alpha value if the cumulative density exceeds the particular alpha value, then the corresponding value of y is k, okay, at the first time. Then if the cumulative probability exceeds alpha at the first time, then the corresponding value of y equal to k, right? Then from we will take this equation star, okay, equation star, and then that is here we can write that sentence, that is the cumulative probability exceeds alpha, then the corresponding value of y is k. The cumulative probability exceeds alpha at the first time, okay. If the cumulative probability exceeds alpha at the first time, that is here less than equal to alpha, right? If alpha the probabilities exceeds the alpha, then the corresponding value of y equal to y is taken as k, okay. The corresponding value of y is taken as k value. Then from equation star we can obtain the gamma value. Here what is star? Probability of y is less than k plus gamma p naught y equal to k equal to alpha, right? And you can write alpha minus probability of y less than equal to k minus 1 divided by p naught y equal to k, right? So this is the most powerful test for testing H0 versus H1 in geometric distribution case. Here is the P1 is greater than P0 case. Okay, next we will solve for case 2. That is a P1 is less than P naught. That is your homework, goods.